Greetings everyone. Thanks for joining us for the explanatory video on residuals in statistics, which is also called the seventh pillar of the statistical wisdom. Myself Aditi, along with my teammates Jasurya and Shreya. Residuals are the leftover differences between what we predict and what we actually observe. Throughout history, these differences, instead of being ignored, have actually helped scientists discover new truths. Residuals are called the final pillar because they bring together the wisdom of all the earlier methods. The idea was first highlighted by John Herschel in 1831 in his book A Preliminary Discourse on the Study of Natural Philosophy. What he said was, if you test an explanation and it doesn't fully match the data, you must study what's left unexplained. These are the residual phenomena. With the help of the example, we can understand it. Imagine you explain why most people catch a cold in winter by saying because it's cold outside. That explains some of it, but not all. If some people get sick in summer too, the residual phenomena makes you ask, what else is happening? Maybe it's about the viruses or hygiene. That's how new discoveries are made. Let's see how the idea evolved. Ether hypothesis was scientists one believed that light waves travel through a substance called ether. Even though this was wrong, it forced them to question the unknown. Example what we can take here is like believing a car runs on magic dust. Wrong. But it pushes you to ask what really makes it move. Methods of residues given by the John Stuart Mill. What he said is if you remove the known causes, whatever is left behind must point to new cause. Example what we can consider here is if your phone won't charge, you test the cable and charger. If they are fine, the leftover problem points to the phone itself. Influence thinker says that this way of thinking inspired Darwin in studying evolution and Mill in logical reasoning. Statistical use here is in statistics, residual is equals to observed minus predicted. If our model predicts someone's height as 170 centimeter, but the actual is 175 centimeter, the residual is plus 5 centimeter. Discovery what here gets triggered is many times. Looking at these leftover differences helps us discover the hidden patterns. First, people assumed Earth was a perfect sphere. Then came a more complex model. Earth as ellipsoid slightly squashed at pole. Here, if Earth is squashed, y is greater than 0. If Earth is elongated, y is less than 0. Method is scientists measure arc lengths of 1 degree at different latitudes. Key question what here arises is if we look at the residuals from this sphere model, do they rise or fall when compared with the sine square L? An easy example which we can take here is it's like guessing everyone's shoe size is the same sphere model. When you check the real data, the differences, that is the residual, show that the shoe size actually depends on height or age. This is the ellipsoid model. Boscovich showed how residuals reveals new truth. The line xy equal to sphere model, this is the average arc length. The point A, B, C, D, E is equals to actual data points. This is their differences are residuals. Line GV was his best fit line where he minimized absolute deviation, like balancing the errors fairly. His findings were the residuals sloped upwards. This meant Earth is squashed at the poles. Significance here is this was an early use of nested models. It introduced the idea of regression. Adding extra predictors like sine square L makes the model better. Simple analogy what we can consider here is imagine you assume everyone's exam score depends only on study time, but the residuals show a pattern with sleep hours. Adding that predictor improves your model. The same method was used in astronomy. Problem here was observation showed Jupiter was speeding up and Saturn was slowing down. People worried that solar system might collapse. Early scientists like Euler and Lagrange tried models but couldn't explain it fully. Laplace solved it. He showed that strange differences were part of 900-year cycle, not instability. Meaning, the solar system was stable. The errors was actually part of long pattern. Easy example what we can consider here is think of your weight. If you weigh yourself daily, you might see sudden ups and downs. These are the residuals. At first, it looks like your health is unstable. But when you see the long term trend, you realize it's just normal cycles. In 1899, G. Udney Yule applied the residual logic to social sciences. He studied whether giving more welfare relief reduced poverty or not. He compared poverty in 1871 and 1881 across the district. After controlling for other economic factors, the residual effect showed more relief was linked with more poverty. This became the start of regression analysis and the social sciences. Easy example which we can take here is suppose a school increases free lunches. You expect attendance to go up, but the residuals show that absences still rise. That leftover pattern makes you explore the new reasons like illness or family issues. Now, I would like to hand over the presentation to my team partner Shreya. Over to you, Shreya.
Thanks, Aditi. Now we will discuss on Fisher's innovation on parametric models. Before Fisher, Carl Pearson tried to describe data using very general mathematical distributions. But those were too vague and didn't give clear answers, like saying people have different weights without specifying how. In 1922, Fisher introduced the idea of parametric models. He said, let's describe distributions with specific parameters. For example, normal distribution with a mean and variance, and binomial distribution with a probability. This made analysis easier because we now had a structured way to test the data. The impacts of it were in earlier methods like least squares turned out to be a special case of parametric models. It opened the door for hypothesis testing and estimation. Some examples like instead of saying students' heights vary randomly, Fisher's method says students' heights follow a normal distribution with an average of 170 cm and spread of 10 cm. This structure makes testing much easier. Coming to Neyman Pearson's framework, Fisher's idea was extended by Jerzy Neyman and Egan Pearson. Their main contributions were they gave us the best possible test when comparing two models. This is called the Neyman Pearson lemma model. Also, they gave this likelihood ratio test where this comparison made a smaller model to a bigger, broader model. The key idea was a broader model always fits better, but is this the improvement real or just luck? This test helped us to decide the foundation of modern hypothesis testing. Suppose you are predicting exam scores. Model 1 uses study hours only, and Model 2 uses study hours plus sleep plus diet. Of course, the bigger model looks better, but Neyman Pearson test asks is it truly better or is it just adding noise? Now, coming to Pearson's cheat square test. This is a perfect dice example where Pearson introduced a cheat square test in 1900. The testing was whether to check whether a dice was fair or not. So we roll the dice many times, and the observed values is how many times each face actually come up, or and the expected values are how many times each face should appear if the dice is fair. And the formula we came up is summation of observed minus expected whole square by the expected. If the x squared is too high, it means the dice is probably not fair. Suppose if you toss a coin for 100 times and get 80 heads and 20 tails, the difference between observed and expected is too large. And we can say that the coin is biased in this case. So beyond Pearson, there is another hypothesis that Fisher and Cox gave. Pearson stated that, but then Fisher in the 1920s added a correction to this thesis. He warned about degrees of freedom. When you estimate parameters from the data itself, you need to adjust for it. Later in the 1970s, David Cox introduced partial likelihood methods. This was powerful because the base model didn't need to be fully parametric. Only the extra part needed parameters. This gave us the famous Cox regression, especially useful in survival analysis and medicine. In example, in medical studies, we may not know the full distribution of patient survival times, but Cox's method let us still model survival by focusing only on part of the likelihood, making analysis much more practical. Coming to the residual analysis in diagnostics. So, in modern statistics, residuals are used for checking model fit, and we calculate it by subtracting observed and predicted values and getting the residual value. After fitting a regression model, we plot residuals against fitted values. If the residuals show patterns, something is definitely wrong. The purposes of checking these residuals are to spot patterns, detect unequal variance, and catch nonlinearity. For example, if you predict student scores from hours studied, but residuals show that errors some increase for very high study hours, it means the model is missing something. Either due to stress or burnout, the students were not able to perform. Another example is the Galapagos example is for the residual plots. So the data is species diversity on Galapagos Island depends on the area and elevation. And two models were proposed. First model was linear model where residuals showed increasing variation and not a good fit. Another improved model was log scale model where residuals became much more stable and much better fit. The key insight we got from this example is suggested a multiplicative relationship between different variables. But the limitations were log A and log E were strongly correlated, so it was hard to separate their effects. An example can be predicting salary from age and experience. A linear model may not fit well, but if you log transform the values, the model fits better because growth is not linear but exponential like. There is now coming to these early statistical graphics given by Playfair in 1801. He created the first pie chart. He used it to compare European, Asiatic, Russian, and Turkish empires. The residual idea here showing departures from equality. The significance was this was the start of using graphics to visualize statistical differences. Suppose if you divide a pizza equally among four friends, each should get 25%. A pie chart shows who got more and who got less. The differences are like residuals. Now, next, it will be explained by my fellow team member Jayasuriya. Please, Jayasuriya, now explain.
Thanks, Riya. Starting with the Fars cholera plots, William Farr studied the cholera epidemic of 1848 to 1849. His circular plot combined mortality as an outer circle, weekly deaths shown as the distance from the center, and temperature trends inside the circle. The plot showed epidemic peaks and a possible link to climate. The limitations were Farr wrongly thought cholera was airborne. For later, it was shown to be waterborne. An easy example will be imagine plotting COVID 19 cases along with the temperature. If both rise together, you might wrongly think heat causes COVID. Farr made a similar mistake. Then these graphics were reformed by Nightingale. Florence Nightingale used graphics during Crimean War. She compared mortality in field hospitals versus British hospitals. She used wedge-shaped diagrams to avoid misleading visuals. Her graphics were persuasive tools to push for sanitation reforms. The irony is, fast graphics aimed at science but misled. Nightingale's aimed at persuasion but were more truthful. Easy take will be today we use clear visuals to show government data on pollution. People understand and push reforms. That's exactly what Nightingale did. The seven pillars are supports of statistical wisdom, not wisdom itself. The origins are from same ancient, mostly developed by early 20th century. They are still very relevant in big data and modern times. Statistics is the original data science and it still partners with computer science today. But these ideas are powerful if used correctly and dangerous if misused. If you misuse averages, you can hide inequality. For example, an average income may look good, but the residual differences show some people earn very little. The strengths and challenges of the pillars are aggregation. It simplifies the big data but lose important details. Information. The more the data helps, but after a point, returns diminish. The likelihood is it helps us measure the evidence, but if misused, can mislead. It works well with the data set, but may not apply outside. Regression helps us discover deeper insights by reframing questions, and proper design of studies ensures reliability. Residual helps us compare models, visualize errors, and discover new effects. This all these challenges, strengths, and weaknesses brings us to the call for the eighth pillar. The modern challenges we face are big data and machine learning. We have too many variables. In genomics and ANOVA, we have too many comparisons, and research choices are having some hidden biases. Problem caused by these are sparse data in high dimensions, overly conservative or misleading conclusions, and researchers having bias hidden in their choices. This creates the need for the eighth pillar. In machine learning, if you test too many models on the same dataset, you will always find one that works, but it may be false. This is the garden of forking paths. With that being said, the future of statistics may have possibility of having an eighth pillar, but it's still unknown. But many partial solutions exist, like false discovery rate, Bayesian machine learning, partial likelihood, but no unifying structure has appeared yet. The takeaways are the seven pillars are strong, but statistics is still alive and growing. The eighth pillar may emerge as we solve big data challenges. Just as dark matter explains invisible parts of the universe, the future pillar of statistics may explain hidden patterns in modern big data. Thank you for listening. Residuals as the seventh pillar reminds us that errors are not just mistakes, they are clues to the new discoveries. Statistics continue to evolve, and just like science, it adapts to new challenges. The story of residuals show that by studying what doesn't fit, we often find what the most important truths are. Thank you.